Okay, so we have a second talk right now. We are glad to have Faroogh Moosavian from Oxford, who is going to tell us about spin charge in asymptotically-flat spacetime.
Okay, thank you very much for this opportunity. Sorry, I didn't realize that the weather is like too warm, so here, so I have this. No, it's okay, it's okay. So, oh, okay, this will work. So yeah, I'm going to talk about how to define spin, possible definition of spin in asymptotically flat spacetime. So this is the outline of the talk. Just starting with some motivation, why this is an interesting question. And then to understand the general strategy, I apply this in the case of like non-gravitational systems, most importantly, the Poincare algebra. So here, the concepts that are used are quadrant actions and its orbits. It's related to the dual of any Lie algebra. And then I explain how this can be extended to the case of the gravitation, in the presence of gravitation, starting with the troubles with the BMS algebra, and then how the generalized BMS algebra can be used to define spin, using the notion, a well-defined notion of isotropy subalgebra, and a specific definition of spin. Then up to this point, there is not much physics, just algebra. And then physics enters through the phase space, the concept of moment map. And then once I construct the moment map, I can construct the gravitational the gravitational spin charge. As an application of the formalism, I use this whole formalism to construct the multiple moments of the Kerr spacetime. And then I finish with some future directions for further studies. Okay, so spin is interesting because is interesting in the case of like studying quantum field theory. Fields with different spins, behave differently. So it's reasonable to expect that in the presence of gravity, we have some notion of spin that survives, at least classically. I explain what it means. It's well known that if we include gravity, there might be some murky things happens, and it appears in the very literal first paper on probably asymptotic symmetries is this paper of Sachs, that he says there is no notion of spin for a group that GBM is the BMS group, which is called generalized Bondi-Metzner group. And you can see that here he explains it a little more. So why it's for the BMS group, there is no such a notion. So it's a classic problem, very old problem from the very first paper of about asymptotic. I think these are the very first paper. This and the paper of Bondi are the first papers on the asymptotic symmetries. So it's an interesting problem to study. So usually it's said that there is no notion of spin, classical notion of spin, and this is not correct. Why it's not correct, we can define notion of spin, classical spin for a symmetry algebra G. The basic idea is that we work with the dual of the Lie algebra instead of the Lie algebra itself. So usually in the context of symmetry algebras that we are dealing with, it's of this form, which is a semi-direct sum, I think called factor or quotient part, and there is a normal part. And then the normal part, except in very rare cases, is always an abelian group or abelian Lie algebra. L denotes the Lie algebra of G, and that notation just means that L somehow acts on n by bracket, as the definition of G says. So to this data, usually we attach a spin in the case of Poincare, which I explained. Just a reminder that what is the meaning of isotropy subalgebra means that you have an n which belongs to the dual, belongs to n, to the normal part. This should be n, the capital N is equal to 0. So this is the meaning of the isotropy subalgebra. Analogously, we have concepts about the dual Lie algebra. G is of that form. That form might be a bit misleading, but just for the notation, in the case of infinite dimensional, might not be completely correct. But there are duals of the K's and N's, and instead of the Lie algebra, we have a Lie Poisson structure on the dual. And the K star part somehow acts on the dual of N. What is the Lie Poisson structure? Is if you have two functions on the space of functions on the coadjoint or on the dual of the Lie algebra, and defining a pairing between the Lie algebra and its dual, you can define the Lie Poisson structure by that formula when differential of a function should be thought of as a map to the Lie algebra. So really this bracket that appears here, sorry, what that? Oh yeah. So this bracket is really the bracket of the Lie algebra. So now using this, we should be able to define similar things, but for the dual. Just a reminder that isotropy subalgebra for the dual is defined in a similar fashion, which pick a Q in the dual of N, and then instead of adjoint action, the coadjoint action of the Lie algebra, the x's in the that G part should be K part. Sorry for the mistake. The coadjoint action of that part and Q is equal to 0. So using this, we define a classical notion of spin as something that is invariant under the coadjoint action of N, and also is the generator of the isotropy subalgebra, which is just the analog of the way that we are defining in the usual case. In the following, I will use this definition to construct the notion of spin, classical spin, first for non-gravitational system, and then extension to gravity, in the presence of gravity. An important concept is the concept of coadjoint action and its orbits, which is defined through the same pairing, dually. Dual of the coadjoint action is the adjoint action. So this is the defining relations of the coadjoint action of the group G on the Lie algebra, on the dual of the Lie algebra. And it has orbits, which has initial point P, and any P prime that can be reached by the action of G to P, by coadjoint action of the group G on P is one of the elements of these orbits. So we can choose also, because usually working with groups are difficult, we can have an infinitesimal notions of this coadjoint action and its orbits. In particular, you have the notion of coadjoint actions of the Lie algebra, which is defined again similarly, and the adjoint action is just a white bracket. So how do we classify? One of the important notions is the classification of the orbits, similar again to the classification of the representation theory, at least finite dimensional. We use a notion of Casimir's, but here there are Casimir's functions that are defined on the coadjoint orbit. Their definition is that they are invariant under the orbits, or their level sets determine the orbit. So you bunch of numbers, that is if you construct all of the C's, is a complete set, put them equal to some constant, that gives you the orbit. So now we can apply this in the case of Poincaré. Take the elements, I call them G mu nu, which are dual to the element in the algebra Poincaré. Then just from the definitions, you can read off the coadjoint actions and the Lie Poisson structure, which is just a rename for the coadjoint actions. So you see that these are the classical analogs of the Poincaré algebra. Basically, if we attach an I, we get the Poincaré algebra. So now from this, similar to the usual Poincaré, we have two Casimir functions. There are 10 generators, so the orbits are 8-dimensional, and there is a notion of rest mass. We can perform like a Lorentz transformation to bring in the rest form. So you have a notion of isotropy subalgebra. This is its generator, and it satisfies these relations of the Lie Poisson structure, which is just the classical analog of the usual SO3 algebra, Lie bracket. So this is a perfectly well-defined classical notion of spin. So this observation can now be generalized. But it's not immediate, because in gravity, especially if we have an eye towards quantum gravity, Poincare is just the isometry algebra of some spacetime. We cannot just take that. We cannot just choose isometry algebra of a specific spacetime and work with that and construct spin. We need to work, the only meaningful thing, it seems, that to work with asymptotic symmetries instead. So in the case that I'm considering, only case of asymptotically flat spacetimes below, the first example is the BMS. So if these are the generators of the BMS and J's are the duals, then it's known that the isotropy subalgebras BMS are the solutions of this, as I defined. But for generic M, this does not have a solution. Okay, this does not have a solution, and this is also, it's not our paper. I mean, it's like a very well-known result in the past from McCarthy. For generic M, there is no such, there is no solution for this equation. Sorry, for generic M. So I should be a little bit quick. So a way out is just to consider more general. I mean, one of the cases, it seems that a good case, because it's big enough to give a notion of isotropy subalgebra. So its Lie algebra is written by is given by this expression. So if you have this zeta, which depends on the two parameters, because there are x is the generators of diffeomorphism, and t is the generator of the supertranslations. There are some weights that I just ignored. I haven't included that. So in the definition of the GBMS, it's like conformal dimension something functions on the sphere. So this is the algebra. So this is with respect to a specific choice of a strictly positive area form, and this would be important. The procedure is, as just I explained for the case of Poincare, we take a dual, we construct the coadjuvant actions just from the definitions that I gave you. This is just an integration by part. And then we need to solve this equation here, to construct the isotropy subalgebra. And then it turns out that to be this type of vector fields in the diffeomorphism, which are called, so they are preserving a rescaled form of the, so they, first of all, they satisfy these relations. So you see that the usual bracket on the sphere, functions on the sphere, is just rescaled by a factor of m. And then such vector fields preserve area form, which are rescaled. So these are, so the isotropy subalgebra is part of the diffeomorphism that preserves that rescale area form. So now we can define notion of spin. 5 minutes. Yeah. Sorry, what's phi? Phi is a function on a sphere. It's like used for, so for any function on a sphere, you can, sorry, for any function on a sphere, you can construct such a vector field. So this is, yes, yeah. For any, so M is the dual of the supertranslation, so it's just anything on the sphere. It's not constant or anything.
Supermomentum.
Two.
No, it's called the supermomentum, and you have 8 minutes.
Okay. That's okay. Yes. Sorry. This is a spin. So we can define this quantity as phi, which is through this quantity called vorticity, and then you can show that it's supertranslation invariant, and also it satisfies this algebra, which is the right algebra, because we need to have this rescaled bracket. So this satisfies the two conditions for the definition of the spin. So it's a definition of the spin, I mean, according to our definition. I mean, this usual definition. Okay. So now we move to phase space. Let me be very quick here. So I mean, up to now, I haven't said anything from where these algebras come. These algebras just given to me. I just want to construct a spin for them. Now, the algebra comes, the physics comes through the concept of moment map. So what is a moment map? If you have a space gamma, which has a action of G space, there is a map between, if this action is canonical, then there is a map, then there is a map from the space to the dual of the Lie algebra, which commutes with the G actions on these two spaces, gamma and G. That's the action of G on gamma is just the action. The action on the G check is the quadrant action. So it just commutes with this. Gamma for us is a gravitational phase space, which is defined by, I mean, I'm using the notation of Pranzetti and Friedel. So this phase space is called a strongly, I think they call it strongly non-radiative phase space, and then you put this dual mass equal to 0, then there is an adjective electric, I think they call it. These are the usual covariant version of the quantities that appear in the asymptotic expansion of the metric. Okay, I said that gamma is non-radiative. So the gamma is characterized by these quantities, covariant mass, covariant angular momentum, or angular momentum. And you can construct, just because the action of the GBMS on the phase space is of, for M and this quantity small j is of this form. So now if you compare this action with the action, let me go a little bit, with this action here, you can immediately read off the moment map, which is this expression. This u is the usual time coordinate. And now we can construct the gravitational, because we have a map from the phase space to the dual, we can pull it back, this quantity, to the phase space and construct the charges, which by definition, because the moment map is G covariant, this satisfies this relation. This, according to this program, completes the construction of the spin. As an application, this is, so one of the quantities that appear is vorticity in the construction of the spin. So we use that quantity to classify, basically, or construct all the Casimir functions on the quadrant orbits of GBMS. So these functions are of this form. You remember this definition of this vorticity. So any quadrant orbit is a level set of these Casimirs. So now, again, we can pull it back to the phase space and construct the Casimirs on the phase space very explicitly. And now we can compute them very explicitly for the Kerr spacetime. If you remember, these two were the things that parameterizing the phase space, which M and A are the usual parameters that appear in the Kerr metric. And if you compute the integrals that I wrote, this thing here, this integral, you can see that these are the Casimirs, very explicitly in terms of M and J. So in particular, the mass and the reduced angular momentum of the Kerr can be completely algebraically be constructed in terms of these Casimirs. So it has some relation to the Noether theorem that says that all the multiple moments, the spin type and mass type multiple moments of the Kerr black hole, I should say Kerr spacetime, or black hole, whatever, can be constructed from this M and A, or M and not reduced version of A, which is J, the angular momentum. And this is kind of reflected in our construction, because from this formula, you can see that all the Casimirs can be constructed in terms of the zeros and the first two Casimirs. So in principle, we can construct all the, if the formulas is used, the formulas that given in the paper of Gerok and others, you use those formulas, you can construct these multiple moments in terms of the Casimirs of the GBMS very explicitly. I mean, this is the formula. And that seems to be something interesting. Some future directions. most importantly, how to quantize stuff. I mentioned that this is true for the strictly positive area form. So, but we know that because I haven't explained how the Poincare can be embedded inside GBMS, but for any metric, even not necessarily the round one. But the question is that the thing that I explained is the analog of the massive representations. So the question is that what are the analogs of zero and negative mass representations? Somehow using this, GBMS can be singled out, maybe. And what about other asymptotic symmetries? I'm not sure whether there is consensus about whether they're algebroids, whatever. Okay, great, thank you.
Thank you very much for the great talk, and thank you for the effort of keeping it in the time. Are there questions? Yes, I see two, at least.
Well, you can start. Hello. Sorry, I was gonna ask whether you can test your proposal for some dynamical setting like black hole scattering or mergers.
I mean, the whole setup is based on asymptotic symmetries. If you can give me some information in that setting in terms of these asymptotic symmetries, I can apply this and maybe get something out of it. Okay. I'm saying that if the asymptotic symmetries correspond with the 80 phases law, I can apply this formalism to construct that. This formalism,
Okay, so I'm curious about the relation with the usual notion of spin in Poincare. I mean, like using the Pauli-Lubansky. So does it how does it fit in this new way? Right? I'm not thinking of like metrics. I just like if I have a spin-2 particle, so spin-2, you know, it's determined in terms of the value of the quartic Casimir. So what are the labels now in your classification for a spin-2 particle? No, but I want to know the value of these Casimirs that you have given. No, but I'm just asking if I wanted to describe like Poincare spin-2, but in terms of BMS group, what would be the values of the Casimirs I would have to consider? Yeah, I'm not sure it's clear. I mean, maybe people working on BMS representation can tell, but to me, it's not clear how spin-2, I mean, lift to some values of. You know. No, but because you started with the statement that the quartic Casimir in Poincare was not a Casimir in BMS. I think that was your starting point. Well, do you know the Pauli-Lubansky W mu W mu? Okay. Yeah, I think you haven't answered my question of where can I find spin-2 particles in these representation classic. Yes. Even classically, I mean, even classically. It's okay. It's okay.
So yes, maybe it's a technical question. I'm sorry if I'm mistaken from the notation, but could you show us your transformation, for instance, of the mass aspect, please? Because to my impression, so to save a bit of time, because to my impression, you are lacking a term in this transformation. Mais show the yes, but so you are defining your covariant momentum aspect in the nomenclature of Laura and friends, and then you are saying that you need shear to define these quantities. If the shear is absent, the shear is CAB. If you don't have a CAB, this quantity, you don't care about even the transformation. They're transforming like in Poincaré, but you break Carroll boost invariance or translation or supertranslation invariance, doesn't matter. But no, the thing is that from a BMS transformation, you will turn on which it's really as JA. This JA couples with derivative of the supertranslation parameter in the transformation of the body mass aspect, which is your small m. Yes, it depends on the news. See. Sorry? Okay, fine, but okay. In this transformation, I should find somewhere a plus IA dA of what's your parameter T, capital T. I did it many times, yes, I know. Yeah. In the transformation of the mass. Okay, so that, but fine.
And there was a question over there.
Regarding the multiple expansion, using this procedure, can you compute the multipolar expansion for the magnetic mass? For example, for Kirchhoff-Nash magnetic mass, or do you mean that? Right. That is the dual, right? Yeah. That is the dual mass, right? Yes. But you can't set it yeah, but in general, it's not zero. Yeah, I'm saying that it's kind of space you have an action. But if you turn on and I don't
Simon has a question over there, and I have the two microphones. Can you pass? Can you help me?
Sorry.
So yeah, just to make sure again that I understand what's happening. So the condition that is your spacetime is strongly not radiative, you impose it such that the transformation laws of the mass aspect and angular momentum aspect match the coadjuvant action of GBMS, right? Okay. But I believe that there are also other ways to get covariant momenta without imposing some no radiation condition by introducing. Oh, I believe it's of this form without killing radiation. Yeah, exactly. Yeah. By introducing some vacuum structure, essentially, with the UV field and.
But the transformation properties of this is written as paper of Daniel and Laurent, gravity symmetry. We can just. I think we tried it, but we didn't get that expression. This expression. That was the reason that at the end we imposed that condition.
Yeah, but you need to introduce extra structure compared to this paper. Yeah, like a UV field and the vacuum.
Like this one, where this states are M and J. Or there should be some liquid data.
Yeah, there are some extra fields, but this.
So that probably is of the transformation worldwide, but actually, that does not have an analog in the. Well, I don't know what's the analog of that.
It would be Weil BMS.
What is Weil BMS? Okay.
Have you thought? Have you thought about how this consideration fit in string theory? Because there the spin is well defined. I mean, how do you take this consideration inside string theory? There is what the
I don't know.
yeah, but that means that string theory avoids asymptotic symmetry because it defines the spin.
Terms, so find boundary terms. Actually, there was a little paper of Ted earlier that shows that actually action of the string theory vastly vanishes, but only there are boundary terms that should determine the dynamics of the string. So that's what Bosonic string says before. So maybe those boundary terms can tell us what asymptoticity is.
Okay, thank you.
Okay, so it's time for the break. I feel so. Just something. Just yeah, please. Oh no.